This is columns part 8. Now that we know how to calculate column strength the hard way, let's do it the easy way. If you Google column strength calculator, go to the Cornell University website, which is courses.edu/ARCH264/calculators/example 7.3/index.html. Then you can choose a beam cross-section, beam length, end conditions, and then press update. Let's do that. Here we go. There we are. That's where we are. Okay, so let's choose this. We've got this W4x13 chosen here. W4x13. Okay. They say it's a section type W4, W8. Let's see. We have a yield strength of 36,000. They say KSI, that means 1,000 pounds per square inch. K means 1,000. Okay. Its cross-sectional area is 3.83 square inches. And they're saying the modulus of elasticity is 29,000 pounds per square inch, or 29 million pounds per square inch. They taught us back in my college days about 30 million. I guess steel's not as stiff as it used to be. Okay, the least radius of gyration is 1 inch. Let's see. We go down here. Okay, I've already got fixed at both ends clicked. It gives you a default, I think, pinned at both ends is what they normally, is what you'll find it on with K equal to 1, but we want fixed at both ends because that's what the failed component of my tail boom was. It was welded in place. So let's just leave that default length of 10 feet at 10 feet. We can choose whatever we want, but we'll leave it at that for now. Now let's hit update, and it tells us that the capacity of this W4x13, which is a 4-inch high beam that weighs 13 pounds per running foot, the capacity of this section, this 10-foot long piece of this, is almost 60,000 pounds. KIPS, KIPS, that means 1,000 pounds. That's engineering lingo. Okay, based on a slenderness ratio of KL/R equals 78, that'd be 0.68. K is, or 0.65. K is 0.65 in this case, times L was 10 feet, which is 120 inches, divided by R, which was 1 inch, and you should get 78. I guess I haven't done it yet. This is a fine time to be checking out something like this, isn't it? 0.65 times, what was that, KL/R. L was 120 inches, equals, divided by 1, equals, yep, 78. Just like they said, the slenderness ratio is 78. Okay. Ooh, sorry about bumping the camera there. I normally do this with my iPad, but I'm using the iPad to make this video. That's why we have to squint our eyes to look at the calculator. Okay, and an allowable stress of 15.65 KSI. That means 15,650 pounds per square inch. That KSI is more of that engineering lingo, 1,000 pounds per square inch. Okay, and you can just pick out any old beam you want, well, as long as it's on their list. Of course, they don't have the one we needed on this list. The one that was part of the steel stork. What we do find by toying around with this calculator is that it's standard procedure to allow short columns much lesser loads than the theoretical Euler equation loads. Now, short columns are allowed much greater loads than long columns are allowed, but still they're allowed way less than what the Euler equation calculation will turn out to be. Okay, and we also find that beams with the same slenderness ratios are allowed the same stress, regardless of what their other characteristics might be. Big beams that are real long and have the same slenderness ratio as a smaller beam that's shorter, the cross-sectional area of that beam will be allowed the same number of pounds per square inch. Of course, the big beam will carry more of a load because there are more square inches, but it's the same stress, the same number of pounds per square inch if the slenderness ratio is the same. Okay, the following table, this is a table showing the data for several examples. Okay, here's the beam description. This W4, W8, W4 by 13, that's what we just looked at on the calculator. It has a weight of 13 pounds per running foot. That's why they call it W4 by 13. Okay, as you can see, this W10, W12, it's a 10-inch high beam, but it's only 12 pounds per running foot. It has thinner web and flanges than this W4 by 13. And here's one that's 61 pounds per running foot. See, that's the weight of the beam, pounds per running foot. And we've even got one down here, 90 pounds per foot. It's a 30-inch high beam. Obviously, we're not going to use any of these on our airplane, but we can still glean information from this that's very valuable to us in designing our airplane. Okay, here's the cross-sectional area. The one we just figured was 3.83 square inches. And you see this 90-pound one is 26.4 square inches cross-sectional area. That's the area of the other beams. The radius of gyration, remember the calculator told us that a radius of gyration was 1 inch. Well, here's another beam. It's a higher beam, but this is the least or the lesser radius of gyration. You're going to have two radii of gyration, one about the x-axis, one about the y-axis. What we're concerned with is the weaker of the two, because that's what determines how strong the column will be. It's like the weakest chain or the weakest link in a chain. You can have a big old logging chain, but if it's got just a little rinky-dink ring out of a Cracker Jack box somewhere in the link, you're going to have a weak chain. And that's kind of how this beam is. It's real strong one way. It's 12 inches or 10 inches high, but it's not as wide as this beam. And consequently, its radius of gyration is not as great, or its lesser radius of gyration is not as great as this one's lesser radius of gyration. And here are the radii of gyration of the other beams. Okay, and this, we have the moment of inertia here. 3.9 is what it was for the beam we punched into the calculator. We have 115 moment of inertia for this 90-pound beam. Okay, and we chose these different lengths. I just punched around a bunch of different lengths until I got a bunch of different columns that had the same slenderness ratio. So they all have a slenderness ratio of 84.5. So this W10 by 12, which isn't very wide, it's like a tall skinny eye. Okay, it has to be the shortest beam out of this list to be able to withstand 14,800 pounds per square inch. See, they're all allowed a stress of 14,800 pounds per square inch because they all have the same slenderness ratio. They're not all the same length. The beam that has the smallest radius of gyration here has the shortest length. Okay, and here are the allowable loads, what the calculator says you're allowed. anywhere from 52,400 pounds for this one. Okay, an 8.5 foot long W10 by 12 is allowed 52,400 pounds. Okay, up to 390,000 pounds for this 90 pound per foot beam. Okay, and here are the calculated Euler loads. You won't find this on the, well, you may find it on another calculator, but not the one I just referred to. It tells you the allowable loads. These are the calculated loads. This is what you get when you use this equation. And I used 4 for N. They're saying 0.65 for K, which means 1 over 0.65 squared, which is not going to be quite 4. I haven't figured it out, but I used a slightly different K, slightly different factor for N conditions, but we're talking about fixed at both ends. Okay. Let's see. And I used 30 million pounds per square inch for the modulus of elasticity. That's the first number I learned, but nowadays they're saying 29 million. Steel's not as stiff as it used to be. Okay, and so I did these calculations by using this equation. Okay, and I got 300 and, let's see, let me answer this phone.